most dreaded 10 weeks. With all the knowledge and limited skill set, we had to go through with this. The adrenaline and that excitement. We're not worried about losing. We're willing to do anything. It's absolute chaos out there.
Once we heard about this year's challenge, the team on the mobile engineering side took in consideration 5 design principles for effective control over algorithm. Simplicity, usability, familiarity, and consistency. We designed the Android application to have 2 main components, control and connectivity.
For our Bluetooth window, we have a list of previously paired devices. We also have simple buttons to scan for nearby devices as well as a disconnect button. We also implemented a 5 reconnection mechanism in cases of accidental disconnect. And we also have a message component for us to debug and to check what are the messages that have been sent and what are the messages that have been received.
Moving on to the control component. As per the rigid rules of R1, we have a grid adhering to the simplicity and usability principle. Within the grid, we can place infinite obstacles by simply clicking anywhere. By tapping, we can shift the obstacle faces. Additionally, dragging features are enabled to change positions or remove the obstacle. Intuitive dynamic control of the robot can be assured using the control and reset buttons that have forward, reverse, left, and right buttons.
Some of the challenges we faced include making a robust connectivity. And in terms of the live update of the robot, we have to liaise with both the STM team as well as the RPI. We have to coordinate with the RPI team in order to get the message protocol out so that we know the different kinds of headers and payloads to update accordingly. For the STM itself, we have to liaise with the STM team about the turn radius of the robot so that when we do a live update of the grid, we can also update the correct distance properly.
Being part of the hardware programming group, my main focus was on the tuning of the robot to ensure that it can carry out the fundamental movement. So for the straightforward and the turning, we have actually improvised 2 methods. One is the delay using the OS, and the second was the use of gyro. With that, the robot can now do all the fundamental movement to move through the maze and the race.
To ensure our STM manages communication in and out of the chip well, we fixed the 4-character limit for all communication. The first character defines the direction of movement, while the last 3, the magnitude of movement. This provided us with enough precision, consistency, and effectiveness to execute tasks. We also understood the misalignment of wheels and the uneven build of the robot, together with the gyro placement, affected our precise maneuverability. Hence, our team decided to have the robot move in the reverse direction to provide accurate turns and instrument movements.
To simplify calculation and improve efficiency, we created a virtual representation of the arena using a grid system. And on top of that, we specified that the robot should move in 4 directions only: north, east, west, and south. And we made use of the A-star algorithm to calculate the grid cells that the robot should traverse to reach at an ideal position for image recognition for each obstacle.
To determine the sequence of obstacles to visit, we are using both the nearest neighbor algorithm and the brute force algorithm to find the path. We start by finding the target location of the robot in front of the obstacle. These target locations are passed to the algorithm to find the shortest path to traverse, and the minimum of the result are chosen as our path.
To visualize the path and the robot movement, I also created a web app called MPP Simulator. The simulator is simple, lightweight, and portable. It takes the JSON output from algorithm run results, and it displays the obstacles and the path of the robot, which is very helpful for us to diagnose the algorithm results and the obstacle settings before the actual run.
For image recognition, we made use of supervised learning and labeled the images with bounding boxes using robots. With the help of data augmentation, we were able to increase the diversity of the training data set by applying specific transformations to the images. This helped our model to distinguish between the different classes and image IDs based on distinct features, instead of only recognizing images within the training data set. This also made it easier for our robot to identify and recognize image IDs across different lighting conditions and angles. Finally, we trained our model using YOLO V5 object detection model, and our robot is now ready to recognize images.
And finally, we had to bring all of this together.
As the communication specialist, it is my responsibility to ensure that all the devices get the messages and commands that it requires. This is where the RPI comes in. As the central communication hub, it specifies the communication protocols and transfer messages between the STM robot, the Android tablet, the algorithm, and the image recognition server. Everything is implemented in Python. iSerial is used for the serial communication with the STM robot. BlueZis is used for the user communication with the Android tablet. Sorted API is used for the Wi-Fi communication with the algorithm. Image ZMQ is used for image transfer to the image recognition server. With all this, the robot is ready to go.
We tried our best, and with the accurate turns and intelligent obstacle tracking, that's all right. We learn some, we lose some. This was an experience of a lifetime.